Well, Dr. Badger, I think it's time for you to be chairmaniacal. It's 4:05. So.
Very good then. So we will get started today. And I guess maybe first it'd be worthwhile for me to introduce myself, since perhaps not everybody here knows who I am. I'll be chairing today's meeting. I'm George McKee from the University of Wisconsin, but I work at the D3D National Fusion Facility, so literally across the street from UCSD, and I can see some of the buildings on the hill over there. Probably Xiaodi can as well if he looks out and pokes his head up there. And we're Pat and the rest of the SoCal Plasma Group were kind enough to welcome the Burning Plasma Group at D3D to join your sessions, and we're happy to do so. And today will be the first presentation or seminar from this side of Genesee Avenue. And it's my pleasure to welcome Dr. Xiaodi Du, who is a scientist currently with General Atomics. But he comes to us previously after graduating from Tsinghua University in Beijing and doing his graduate student work at the National Institute for Fusion Science in Japan, the Graduate University for Advanced Study, where he worked on LHD and studied interchange modes and LH transition physics. Then went on to a postdoctoral position also at NIFS, and then went on to another postdoctoral position at the University of California, Irvine, jumping over to this side of the Pacific. And there he developed a really impressive, novel and exciting imaging neutral particle analyzer diagnostic system to make energy and spatially resolved measurements of confined fast ion particles, and has also done a number of other diagnostic and scientific activities at D3D, developing a soft X-ray imaging system as well. And now as a General Atomics scientist, he continues to work on energetic fast ion physics, as well as other topics such as plasma disruptions and runaway electron physics. So today he'll be talking to us about multi-scale chirping modes driven by thermal ions in D3D plasmas. Xiaodi, please take it away.
Thanks. Thank you, George, for this introduction. So today I want to talk about multi-scale chirping modes driven by the thermal ion in the plasma with a reactor-relevant ion temperature. I have a lot of contributors. Specifically, I should mention this beautiful measurement is from the DDS, which is supported by the Rongjie, and also the theory and supported by the theory group and the CGYRO simulation from Xiaodi and Huiqian Wang, and also other contributors. And I have a special thanks to the Dr. Zonka and Liu Chen, which teach me their theory and have further discussion and support on this research. So why I want to study this topic? So if you look at this n tau, y-axis n tau and x-axis temperature, so this chart you can see if you want to achieve the Q equal 10, so this is the contour plot of the Q equal 10. So basically the optimum temperature you would have for the minimum tau is around the 35 keV. So that basically means the tail energy of the thermal ion in the future power plant will be very comparable to the energy of the beam ions in the current device, such as D3D, we have the 80 keV beam and the half energy, the 40 keV. So it's also well known that the sub-Alfvénic beam ions can actually drive the EPM or Alfvénic eigenmodes in the mining devices through the high order randomness. So the model also shows the Maxwellian distribution can provide the free energies to drive such things from the radial gradient. So the other important effect is provided by this high temperature plasma is the ion compression effect, which is basically associated with ion transit randomness, which actually can destabilize the discrete electromagnetic eigenmodes in the ideal MHD domain. So the main question is, will the thermal ion with the very high temperature, with reactor-relevant ion temperature, bring the new challenge to the operation of a fusion reactor, which we are not at that regime right now. So it's good to study this topic to understand the future possible challenge we may face. So today I will talk about the multi-scale chirping modes, which is driven by the thermal ions with a very high ion temperature in D3D tokamak. And I would show you the mode have the very strong non-perturbable feature, which means the mode structure can be rapidly changed. And And also I will report that can cause a prompt reconnection. And also sometimes we saw the minor disruption events triggered by this mode. And also we compare this observation to the theory predict Alfvénic ITG. We do recover lots of the features of the AITG. So this is the experiment data we have. So we compare a pair of shot with a matched equilibrium density and heating scenario. You can see this is the spectrum from these two shots. One is you have lots of chirping modes, another have the steady frequency mode. And the shocking thing is that the density is basically the same. And also the inject beam scenario and the power is exactly the same. So we don't have the clearly difference in this density and the power. But if you look at but the question is why the one mode is chirping, another is not. So when we look at the temperature, and the ion temperature is actually 30% higher than this steady frequency shot. So in this chirping mode, so you can see chirping actually have the higher ion temperature here compared with this black line, which is the steady frequency one. And the TE is about the 7% defer, and also slightly higher in this chirping one. So if you look at this trace of the density and look at the mode amplitude, so you can see the chirping mode amplitude is actually gradually increased from the relative weak to the very strong later. And that correlated to the density gradually increase, but you have the fixed beam power. So that gives you the faster slowing down time, which reduced your beta EP. So basically, this is very different with what we already saw. So we saw the stronger mode amplitude chirping mode with a lower beta EP. That is a surprise point when I first look at the data. And then I search the database and do the statistical analysis. So what we found is you can see this chart. Y-axis is the temperature in the plasma core, the ion temperature in the plasma core, measured by the CER. So x-axis is the normal beam power normalized by the density. Basically, you have the lower density in this side and the higher density in this side. So power is need to inject all the time to maintain the high ion temperature. So what we found is basically at the high TI, the mode is stronger. You can see the size of this is corresponding to the density fluctuation amplitude measured by the interferometer. And also the mode appears at the relative high density, as I just showed in the in the previous slide. So that is very shocking because for the EPM type mode, usually what we found is, for example, the energy particle driven interchange mode in the LHD. So the mode is stronger and always appear at a low density. This is important because we need beta EP comparable with beta thermal to drive this EPM type mode, energy particle mode. But this is a completely different story from the EPM type mode. Usually people think that is a fishbowl type mode. So, and also we overlay the 34 randomly sampled bursts and use the normalized time. You can see all this is the magnetic perturbation and normalized to the time, relative time 0 at the peak value. So this is, I plot the lower panel here is the time derivative of the neutron signal. You can see the 0 means no change, and the plus means the increase, and the minus means the decrease. So it's pretty random. So we don't, for this 34 burst, we don't see the clearly neutron decrease caused by this mode. If I do the condition average of all these bursts, you can see the neutron basically goes through the 0. So we don't have, not like the traditional fishbone, we don't have the strong impact on the neutron signal. And the other interesting feature is the mode is actually excited over a very broad K spectra. This is measured by the DBS data. So you can see it's from the IMIC1 mode to the up to the 21 to 21. So I plot this dashed line to reproduce the mode frequency. You can see it's matched very well. And also another interesting thing is before this bursting event, the most unstable mode is actually this medium K theta wave, which also have the chirping character. You can see it's the frequency that gradually drops. And also we can see this stair shaped frequency spectrum, which indicate the perturbation energy actually transfers from the higher K to the lower K in this medium K range. And the other interesting thing is this spacing of the different frequency. For example, this one is about 32 kilohertz. That is the very same frequency with this frequency, which when the mode chirps down and have the relative steady frequency in the later phase. And the other interesting feature we have is for the most unstable, this medium K theta waves, you can see it have the both magnetic perturbation and density perturbation, or in other words, electrostatic perturbation. But you can see when the burst happens, this electrostatic perturbation disappears and dominated by the magnetic perturbation during this chirping phase. So the frequency quickly drops from some value to the Doppler frequency. I will show later. So, and when the frequency chirping ends, you can see the magnetic perturbation disappears, and then the perturbation in this K range start to dominate by the electrostatic perturbation. There is a transfer from the electromagnetic dominant perturbation to the electrostatic perturbation. Let me just summarize this, the K elements of this observation. So we have the most unstable mode from the m equal 7 to the m equal 11 range. For this K theta range, and that have the both strong electromagnetic and electrostatic. And we have the frequency of the 1-1 mode actually as the lowest frequency actually match the frequency spacing between the medium K waves, suggesting that the trigger probably related with a nonlinear energy coupling. And also we saw the clearly transition from the electrodominant perturbation to electrostatic, just which correlated with this frequency chirping. So what this mode do to our plasma? So we actually saw the magnetic minor disruption occurred at some disruption, some chirping events. So here is one example. You can see we have this chirping mode here, and the one at the end of chirping, this one triggered a large magnetic perturbation here. And at the same time, you see the density spike and the electron temperature drop to the 100 eV, and the ion temperature drop a lot. And also we have the ID spike, which usually indicate the redistribution of the plasma current. So this is all the typical features of the minor disruption. And we have the beta n equal 2.0 at this timing, which is still well below the ideal beta limit. So the question is why some chirping modes trigger the minor disruption event, but not the other? Why this one is so special? So to answer this question, we look at the Q profile. We look at the Q profile of this event, and this event. You can see the black is this one, and the blue color show this one, and the last red before minor disruption event is a red color. We see the Q equal 1 flux surface is gradually moved outward, and the Q equal 2 and 3 surface is pretty much similar. Let me show what the mode structure looks like. So at the very beginning, for example, this guy, I plot the contour of the temperature fluctuation measured by the electron emission. So y-axis is R, axis time. So, and also I overlay the magnetic perturbation as a black line here. So you can see it's oscillate together with the electromagnetic with the temperature fluctuation, and at the same frequency. And the peak of this perturbation is very close to the Q1 flux surface. And the mode structure, you can see the magnetic perturbation becomes stronger here, and also the mode is slightly expanded, but still very near the Q1 flux surface. So this is basically shown there is there are no clearly non-perturbative features in this burst. The mode structure is relatively fixed. If you look at this perturbation, which is this bursting event, which is relatively close to the minor disruption event. So the first thing, the Q1 moves a little bit outward, as I showed in the Q profile. So we can see again. So when the magnetic perturbation becomes very strong here, we saw the temperature fluctuation strongly expanded to the plasma edge. You can see also here. And when the micro-turbulence disappear, we also don't see the clearly temperature fluctuation. And the other interesting thing is if you look at the edge around the critical 3 flux surface, we saw this phase is the temperature fluctuation, the phase of the temperature fluctuation have the inverse feature. We have the pi phase jump near here, but that appeared very short, in a very short period, and that disappeared later. So we think this is probably a feature of the change to the Tyrian parity and the feature of the magnetic reconnection. But the happening of this reconnection is so fast, we think that is probably the Alfvénic fluctuation induced magnetic reconnection, which is very similar with the paper proposed this idea in the simulation. I think there is a question from Patrick.
Yeah, there is. So just waiting to complete.
Yep.
Yeah, just so thank you. Going back one or few slides when you were talking about nonlinear couplings, of course, and particularly the 1-1 and all that, it begs the question is what do you know about zonal structures driven by these modes? And I mean, here you would have candidates, both zonal flow, corrugation, and zonal field would be potentially rather important. I mean,
the answer is we don't know. I'm sorry. So, but that's a very, very important thing we should measure in future. But at present, we don't have the data on that. But that is very important. Yeah, let me continue this. So yeah, we have the reconnection. Magnetic reconnection happens very fast. That's you can see it's basically the time scale of 0.1 millisecond or even shorter than that. So let's see what's happened for the last one, which really triggered disruption. So we have the more systematic magnetic topology change in this case, and you can see the as a magnetic fluctuation measured here, and we have a phase shift, a pi phase shift jump from across the critical 2 flux surface here, and also you can see here across critical 3, we have the very large, very clear pi phase jump across this flux surface. So that basically indicates there is a multi-helicity element chains at the plasma edge, which is correlated with this Alfvénic fluctuation, which lead to the further disruption phase. So in the previous experiment, we do measure how the plasma goes disruption. So you can see this is a soft imaging data perturbation of the soft X-ray emission, which is well aligned with the critical 2 flux surface. Red and the blue here shows the plus and minus of flattening of the profile, which is give you a plus and a minus value compared with the equilibrium. And then you can see it's aligned with the critical 2, also critical 3 flux surface here, and also the extended to the critical 4. So, and that is observed right before we have the disruption. That basically tells you the multi-helicity element chain in the plasma edge is a cause of this major disruption. But I should point out that this is distinct from this kind of picture from the Tyrian mode and the lock mode physics, because the happening of this reconnection is much faster compared with you see this growth time is something like in the 300 millisecond growth time and lead to this disruption event. But now we have this, it happens less than 1 millisecond. So that is a much, I would arguably say this is more dangerous than the traditional Tyrian mode and the lock mode physics, which lead to the disruption. And actually this kind of the very fast magnetic reconnection event was observed before in the LHD, for example, in this bursting mode. This is also similar with temperature fluctuation. You can see the phase is basically the same before we have really goes into the bursting phase. You have the interchange tap or kink tap mode structure. And then once it enters this bursting phase, there is some very complicated physics there. And then we go the reconnection. You can see the pi phase shift start to persist across the later part of the burst event. And you can see the mode structure is plotted here. So that is you have the clearly pi phase shift there. And this is also recently observed in the abrupt large amplitude event in GT6U, which is usually called L. So what they saw is also in a very short time scale. This is the magnetic perturbation energy. It quickly grows, and at this timing, they saw the island formed in the multiple rational surface. You can see also here from the magnification tracing. So this they consider this as the cause of the loss of the neutron signal. I will not go to detail. You can look at the paper published in this one. So let's go to the last part of my talk. So how we understand these instabilities. So because this is in a very high ion temperature regime, so we naturally look at this ITG branch and how they transit to the KBM branch. So the ITG branch is basically destabilized by the I. And but if you further increase the beta of the ion temperature, you're basically stabilized by the finite beta effect. And then the KBM branch, the growth of KBM just very large compared with ITG. So that is give you the electromagnetic perturbation, which is the counterpart of ITG. So the for the KBM branch, you can see the clear feature is the KBM have the real frequency in the plasma frame, which is around the ion diamond frequency. So when the pressure goes really high. So this is the data we have to we can actually this is the bursting events, and we can actually plot the Doppler frequency as this dashed line, and calculate the ion diamond frequency. This is the calculate basically mapping the measure the TINE to the reconstruct equilibrium, and then averaged over the cubic Grunfeld surface. So this is pretty good reproduce the initial frequency of the mode before it's really tripping down. So basically we have the initial frequency very much like the ion diamond frequency in the plasma frame. And when it chirps down to the Doppler frequency here. So, and also I should mention a wave probed in the ion diamond direction toroidally and the co-IP direction toroidally. So, and why it's called the AITG but not the KBM in this case? So according to the Zonka theory, this two published paper, actually the 2 decades ago. So you can see the quote from that paper is when the diamond effect is very strong. So now the mode, for example, BAE, KBM, BAE is pure. In that sense, it's better described the Alfvénic ITG. So here's one example. You can see that this is the dispersion relation of the KBM going like this solid circle, and this crossing markers is a BAE. So it will cross at some frequency, which is related with this omega, with the temperature gradient. So once this coupled happens, so basically you will not distinguish it's a BAE or it's KBM. So that's author claim. You should call it Alfvénic ITG. So it gave you some analytical form to study this to tell you when this Alfvénic ITG can happen. So it's just a simple equation we can check in experiment. So what do we do here to identify mode? We do 3 things. First thing is we will demonstrate you the thermal ion can actually satisfy the transient randomness condition, which is very important because the ion temperature goes high. It actually can run directly with the drift waves. That's the physics. That's the key physics of the Alfvénic ITG. And also I will show the KBM is found to be linearly unstable over broad K spectra, which is predicted by the CGYRO code. And at the last, I will show you this coupling between the KBM and the BAE is indeed observed in experiment using experiment value. That's theoretical criteria is actually satisfied. Let me go through these 3 points. So the first thing is we calculate the y-axis here is the energy and the axis R. So we calculate this transient randomness condition, and you can see this blue dashed line is a phase space where it can resonate with the frequency in the plasma frame. It's basically the ion diamond frequency. So for this is the blue, for the blue dashed line is for the pitch 0.7. And the green is for the pitch 0.8, another pitch. You can see for the more passing particle, we need a lower energy. Yeah, that's really simple because it's just travel faster in the parallel B direction. And then you can see I plot the thermal ion temperature measured by CR. You can see it's basically carbon temperature, but we think that is the same with ion temperature. So this is this line. And also I plot the shaded region as a thermal tail of this one. So you can see it's basically across this blue dashed line, the green dashed line, and the red dashed line in a different radial location. That indicates that we do have the resonance condition satisfied when the temperature goes high, especially in the plasma core. So this is the key element of the AITG theory, which actually emphasizes the importance of this thermal ion transit resonance in the plasma core, which we would expect a lot in the future reactor. And the CGYRO code actually predicts the KBM is linearly unstable. So you can see if we treat the fast ion as just use simple Maxwellian distribution, the peaking at 40 keV, it's average temperature, and we have the growth rate something like this purple line here. It peaked at the k theta rho around the 0.1. So if we remove the fast ion contribution and just look at the thermal only, without any fast ion, but it also reduce the pressure, which is observed in experiment because it remove the fast ion contribution. So we have the k theta rho I peaked at the 0.3 for the linear growth rate. So that basically this mode number range, you may remember that is the most unstable mode we observe before each burst, low end burst happens. So and also for this mode, for this instability, we found when the beta E increase and the growth rate increase, and also the gradient Ti increase, you see the increase of the growth rate. That's a typical feature of the KBM. And also we actually compared it into the mode structure, not shown here. It's consistent with the KBM. And for the theory part, so we just simply use this equation to show actually the eta I is exceed the predict critical eta I, which the ion transit resonance will become important. And also when we calculate this gamma frequency compared with this diamond frequency square, so that's basically the same level, and this ratio give you in experiment that is really close to 0.5. So we do have the coupled condition there. So let me summarize my talk about this. So we found the mode propagating in the ion diamond direction, and with a frequency really close to the omega star I before it chirps down. And we saw the excitation of the mode requires to exceed the certain TS threshold that is observed in experiment. And the plasma regime is close to, but below the ideal MHD beta limit, which is basically a KBM feature. And the wave actually can run with the thermal ion transit frequency because of high end temperature. And also, I should emphasize the mode structure shows very strong no perturbative features. This is clearly indicate the wave particle random interaction is important. Because that will, but if you just consider the MHD, that will not give you any change of mode structure until the wave particle randomness enters. And also it's consistent with the linear analysis using the CGYRO code regarding to the both broad case spectra for the KBM and also the TI, nabla TI and the beta dependence. And I should also want to emphasize it exceeds the theory predicted II threshold to satisfy the criteria for a strong coupling between the BA and the KBM. So towards the future, the mode is unstable at the fraction of the ideal MHD beta limit at the reactor-relevant ion temperature, and it can lead to the minor disruption event through the very fast magnetic reconnection and stochasticization. And their manifestation in future reactors should be carefully studied. And you can read more details in this recently published paper. Thank you.
Okay. Well, thanks very much, Xiaodi. That was a very impressive tour de force on these modes that, well, maybe have been around, but you have much more depth in your measurements here. This is great. So I'd like to open up the talk for any questions or comments from anyone in the audience. So Pat has something.
Yeah, so very interesting. Actually a couple of, I think, of fairly simple questions. If you can change the density profile and you peak it, going back to the very earliest experiments on ITG modes, can you kill this thing? I mean, that would be an interesting test, right? Shoot in a pellet or something, or whatever. You should lower A to I. You're back to Greenwald 84 and the original ITG experiment.
Oh, that's an interesting idea. I probably should propose experiment.
Yeah, well, it's the season for that sort of thing. The other question I had more from a theoretical perspective, I mean, the party line we all espouse these days is, of course, you know, zonal couplings and blah, blah, blah. But listening to the way you describe this mode is very interesting, because with the strong resonance, you should have very significant distortion of the ion distribution function, right? That's what's driving this thing. So you kind of wonder, I mean, in all these simulations, did anyone look at saturation mechanisms? And in particular, is this back almost to ancient history of Sagdayev and Galeev, you know, with the two-dimensional plateau, or some mechanism of that sort? And again, and related, are there experimental signatures of distortion of distribution function?
Yeah, so that probably need to measure the bulk ion.
Right.
So that's a little bit hard for us. So we only measure the carbon temperature, but if the carbon can also run at some phase space, so we may saw something from CR data, I think, from the row spectra. For example, the fitting quality to the Gaussian spectrum, that may tell you. Yeah, I can look at data. That's a good direction to
I mean, the question, what about the simulations, or did they not get past linear theory?
Yeah, there are no linear simulation.
Interesting.
We need help and lots of collaboration with Siri and the simulation group. For this study. Yeah.
Just I'll get to Zayu in just a moment, but just following up on Pat's question and thinking about the ion distribution, would there be any hope of measuring that with the FIDUS system to look for, you know, superthermal ions, or like, especially to compare like your two cases? You have these two very similar plasma conditions, one with and one without these modes.
So that is sensitive to the more sensitive to the energetic, more higher energy. So I think this is a more like 20 or 30 kV range. That's I don't know if FIDA can do the good work there or not. So. So, but I think Sean have the diagnostic to measure the bulk ion probably, right? So I should ask him, but whether they have the good data.
It's conceivable to measure the bulk ion, or kind of the near energetic spectrum. I would think that'd be interesting to compare.
Yes, that's good. That's a good suggestion.
So we have a question from Zayu Lee.
Yeah, a very interesting talk, Xiaodi. I really enjoyed this talk. So I have two questions. One is about the CGYRO simulation, that when you include the fast ion contribution, it seems there is another peak in the even low K range. Is it consistent with the M equals to N equals to 1 mode showing in your spectrum?
That's a very good question. So that's one possibility, I think. Sorry, let me bring this up. Where is the simulation result? So this peak. So the thing I cannot conclude is because the code uses Maxwellian distribution. That's very different from the beam distribution. That's basically what CGYRO do is it introduces another hot species, so which can contribute to this mode growth rate. It's different from the beam distribution. It's very different. So it's I don't know how, if they use a more realistic beam distribution, what the growth rate looks like. But I should emphasize the importance of this, because so if you have, that basically means that if you have the even hotter plasma in future, so you may move this mode to the very low end range. That's you can call it the low end KBM, something like that. So that's interesting to look at in the future reactor if you have the very hot plasma, because this is basically introduce another hot species. That's the 40 keV.
Right,
Yeah.
exactly. So there again, just a question follow up this question. So is there any gyrokinetic code can treat something like the slowing down distribution, like GTC or some other?
GTC can do it, yeah.
I think
without any problem, yeah. GTC can do the more realistic, but you know the problem is computation resources. If you away from this Maxwellian distribution, that's
right.
You need lots of particles to get smoothing phase space distribution.
Right.
So
exactly.
that's super heavy. So.
Yeah. Another question is about the electromagnetic and the electrostatic mode you're showing. Yeah. It shows for me like these two modes are something like one mode is growing and another mode is damping. So is there did you check, is there any interplay between these two kind of modes, like energy exchange or something like that?
Yeah, it's a hard question to answer. So I don't know. I don't know if it's the same mode or it's different mode. It's appeared just one disappear, another grows up. So that's that's really hard to understand. I don't have any understanding of why there is a transition, and why. Another question: why there is a frequency related to the frequency chirping? Because in the EP field, we consider the chirping is like the phase lock. I mean, clump and hole formation, the distortion your distribution, and that give you the chirping of the frequency. It's randomly different phase space, but this seems different. So it's an unresolved answer. I don't know. So if any suggestion and comments on this, I'm very appreciate why this kind of thing can happen. So
okay, yeah, that's all my question. Thank you. Great talk.
Okay, I had a question about, so these modes, it looks like they're occurring at or they're driven largely near the Q equals 1 surface. That's where you saw the delta TE prominent. Yeah. So it just leads to a natural question. Is there any relationship to sawteeth or to reconnection? Or are there sawteeth in these discharges?
So yeah, we actually talked this today with just this morning with Bill about this. So so there's a different possibility. So for the fishbone mode, that is there have two branches of fishbone mode. One is the EP driven, another is more like Koppel's fishbone mode. So that is more like related with ion diamond drift frequency. So with this very low end one, that we think that might be possible with a nonlinear interaction, transfer the energy to the very low end, and then make this kind of because the mode structure is we cannot distinguish which mode. I mean, it looks like kink parity before it induced lots of reconnection. This very low end, that might be nonlinear interaction, nonlinear energy transfer, and the nonlinear excitation for the Koppel's fishbone. But this more higher frequency one have this has a clearly different signature with low end fishbone mode. So for the sawtooth, that's we do not observe any crashing. I mean, according to the each burst. So we don't think that is any connection with sawtooth. But for the very low end, there is still argument. But for this high end, not high end, I mean, it's still low. So for this range, it's we are confident that's the AITJ type mode. Yeah.
Interesting. Okay, we have a question or comment from Pat.
Yeah.
Again, so you mentioned during speaking of Q=1, you mentioned fast reconnection when you were discussing this. How fast is fast?
Okay, so that's a very good question. So the reconnection never happened at the Q=1. You can see the reconnection only happens when this magnetic perturbation becomes strong. Also, the mode structure consistently, mode structure extended to the edge. That's why you have the magnetic perturbation measured at the edge is strong. So that happens across the very low edge directional surface. So if you look at the time scale, so look at here. So this is there is no reconnection. There is no phase shift. So that if you look at time scale, that is this is 1.942 seconds. This is 1.9424. You have a reconnection here, but not here. So you can see the time scale. That is around 0.1 millisecond or less. That is super fast. So you have the very fast change of your parity, and also you can see here it's at critical 2. That's happens same thing.
What is if you translate that to Sweet Parker, how much better than Sweet Parker are you doing? Sweet Parker goes as basically square root of S, right? And so the question is this ideal time scale or even faster than Alfvénic?
I don't know. I should calculate that. That's good. That's good thing to look at. So I don't know this. Yeah, I don't know this answer. This is.
Thanks.
Okay, we have a question from Weisheng Wang.
Hello. Yeah, can you hear me? Yes. So I have a question about just your CGYRO simulation. I just wondering, have you ever tried any nonlinear simulation? And if you tried, what do you see? I guess probably
we have not tried that. So basically, I should give credit to this CGYRO to the Xiaodi. So he actually did this simulation, not me. So we only so far we only did the linear phase. We have not go into the nonlinear phase.
Because I'm asking this question because I think it's a nonlinear simulation of this whatever KBN or AITG. I think people, as far as I know, have a lot of problems with saturation. I mean, that's why you don't have you don't see many like nonlinear results.
Okay.
I think basically somebody called it the runaway problem is basically cost and is saturated at a very extremely high level, and which is normally probably like 1 or 2 order of magnitude higher. So it's unreasonable high. I think one reason is people sort of thinking reason is in this type of turbulence, and then some kind of zonal flow generation somehow is very weak. On the other hand, I think many simulation, this nonlinear electromagnetic simulation, they don't include this low end mode because numerical problems. Okay, for some kind of translation problem, which become extremely pronounced for low end mode. And but we do not include the low end mode, and then actually maybe cause some a problem for the saturation because
that's just what I want to say. So in experiment, I'm rather confident that probably this coupling mechanism, the linear coupling mechanism, is important for the saturation. That's what we put in the paper. That's the speculation, but I think that should be true.
That's
so
true.
You see, so that probably can help your saturation problem.
That's probably possible, and is nonlinear like inverse cascading may be a wonderful important mechanism if zonal flow generation is weak. And then many nonlinear simulation and actually it's difficult to include the low end. That's a related question is because you did this linear calculation, and I'm not sure how you compare with your measurement. basically, but the linear calculation, this spectrum, for example, you picked up like 0.1, but normally this, if you have this strong cascading, and they will cause overall like this spectrum downshift. I think the real spectrum, I guess, you know, you observe from the experiment should probably have some difference offset from this linear spectrum. That's what I guess.
Okay, so you mean this peak location may shift to the low, relatively low case?
Because it's a this nonlinear inverse cascading will normally downshift. I mean, at least for some other typical like ITG, ETG simulation. This is a general, you know, observation. You know, this
so
is nonlinear spectrum is downshifted from the linear spectrum.
So how much usually it's a downshift?
I mean,
it's observable value.
ITG, for example, if ITG case like typical like linear peaked at K pop rho I 0.5, but then downshifted to like 0.3 or 0.2.
I see. So the interesting thing in experiment, the experiment are always much more complicated than the simulation. The one interesting thing is we saw this change of the K. You see it's pretty, actually, you can see it's pretty robust observed also in other cases. So there is a change of the most unstable K actually towards the lower K gradually until you have the low end mode burst. So that's I don't know if that's related or not. So, but yeah, that's also a mystery for us. So why we observe such a thing? And also you can see actually this is also actually happening in the relatively lower frequency range. You see this tendency to go lower K and also the stair shift, downshift of the K.
Yeah. Okay. Okay. Thank you. Anyway, thank you.
Okay. I have one last question. I don't see other questions right now. So my question would be, so you've established that this is sort of very elegantly that this is driven by high ion temperature and probably into the near tail region, and then having these resonances at certain parts of distribution of the distribution function and spatial distribution. So you say, oh, justifiably, this may be a concern for a reactor that would also have very high ion temperatures, but will you have these same kind of resonances? Isn't someone looked carefully at like, for example, an ITER type condition or some other fusion reactor scenarios to see whether or not you've got the gradients and such that would actually drive this?
Yeah, that's I don't know ITER people look at this or not, but yeah, the JET have the same observe same model in the hot ion. I mean, observe same Alfvénic this kind of fluctuation in the high ion temperature regime only. So and they clearly show the data that the related with the mode growth rate related with mode saturation amplitude related with the nabla TI. So I don't know whether ITER have this, but I would suppose that once it enters that regime, probably that will be an issue. Yeah.
Yeah, so it seems like it might be worth someone doing that calculation or estimation, since it seems like it has relatively straightforward resonance conditions there.
Yeah, yes. So just take the equilibrium, and that's pretty simple to calculate with the ITER supposed temperature, something like 20 keV, I guess.
Okay. Well, thanks very much, Xiaodi. Are there any other comments or questions from anyone? And if not, perhaps we will adjourn. Pat, are there any final comments or
other than
mechanics?
Thank you to Xiaodi for an excellent seminar. That was very interesting, and please come back and give more.
Thanks for having me. So I definitely have more to report.
Very good. No, we'd like to hear it, and thank you to George for a bravura performance as chair in his first outing in this job. Badgers are versatile, you know.
Xiaodi was pretty easy to chair for, so it's not hard. And knew you would give a good talk. So yes, thank you very much. And I think this is the last of these SoCal seminars.
It is
quarter
indeed
here.
for this quarter. We will have seminars in the winter. We're looking for victims. All these nice meetings we're having over in, well, not in your place, but hosted by your place are giving me lots of ideas for victims, by the way. So I'll be in touch with you on that. And don't forget, Omicron is on its way up. So I think we're going to be continuing in Zoom mode for the foreseeable future.
The Zoom will be on Zoom, I agree. Yeah, well, it seems to work quite well. So yeah.
True.
Okay. Well, again, thanks, Xiaodi. Thanks, Pat, for hosting and us for joining. And everyone have a great holiday and see you soon.
Bye-bye.
Take care.